Another lecture. Now that we understand how neural networks learn, it's time to get hands-on. So this week you'll start building models using Keras. We'll also introduce how to monitor a model's performance using validation data and the accuracy loss curve. So this will prepare you for the next week where we will talk about optimization and ways to regularize your model. So training a neural network, as we said before, is an iterative optimization process. So it begins by initializing all the weights randomly, right? We're talking about the weights, right? And then in each training iteration, we perform a forward pass, as we said before, where the input data is passed through the network to produce predictions. We then compute the loss, right? And the loss measures how far the predictions are from the actual labels. And then after that, the network performs a backward pass, also known as backpropagation, which we've seen last week, which calculates how each weight contributes to the error. And then using these gradients, we update the weights to reduce the loss. And we said that we use an algorithm that's called the gradient descent to do the weight update. And then this process is repeated over multiple epochs, right? And each epoch is representing one complete pass over the entire training data. And this cycle right here allows the network to gradually learn better weights that improve performance. So before training begins, we must make several key choices that define our model and how it will learn. First, the architecture. So how deep is the network and how many neurons are in each layer? So a shallow network might be too limited, while a deep one can be harder to train, right? And then the second choice will be activation function. So we talked about ReLU, which is commonly used in hidden layers, and we talked about things like sigmoid or softmax, which is used at the output, depending on the task that you're trying to solve, right? And then we must decide how to initialize our weights, right? So we typically start with a small random values to break symmetry, using methods like Xavier or He initialization, which try to draw values from a distribution with zero mean and a specific variance to ensure signal flows remain stable as it propagates throughout the network's layers, right? And then finally, we choose some training hyperparameters, which we'll talk about more next week. So things like the learning rate, and then how many examples to include in each batch, and how many epochs to train the model for. So these decisions impact the conversions process and the performance, and often requires careful tuning, which we'll call hyperparameter fine-tuning, and we'll discuss it next week. So let's clarify two important terms here, the difference between an epoch and a batch size. So an epoch refers to one complete pass through the entire training data, right? So if you have 10K or 10,000 instances or training examples, one epoch means the model has seen all the 10,000 once, right? However, training on all 10,000 examples at once can be inefficient and memory intensive, right? So instead, we divide the data into smaller groups called batches, and the batch size determines how many examples are used in one update step, right? And so, for example, with a batch size of 100, right? If the batch size is 100, then we would perform 100 weight updates per epoch, right? If we had 10,000 training examples. So this technique is called mini batch training, and it balances efficiency and converges stability. So it's a foundational concept for scaling deep learning to large data sets. So as a model trains, we monitor how well it performs by tracking metrics like the loss or the accuracy across multiple epochs. So the training set, which the model learns from directly, and the validation set, which the model never sees during learning, but it is used to evaluate how well the model is generalizing. So remember we talked about the validation data before, right? So it is that held out portion of the original data set. It is not used to update the model's weight, right? Instead it serves as an independent benchmark to assess the model's progress after each epoch. So by comparing the training and the validation performance over time, we can decide whether to continue training or stop or make any adjustment. And this process is essential for building models that perform well on new and seen data. So a critical part of evaluating your model is watching for what we call overfitting. So this happens when your model continues to improve on the training data but starts to perform worse on the validation data. So you typically notice this in the loss curve, or where the training loss continues to decrease, as you can see right here. So this is the opposite. This is the accuracy. So you can see that the training set keeps improving. The training set accuracy keeps improving, whereas the validation set accuracy is degrading right here, right? So here you know that this is a red flag at this point right here. And this means that the model is starting to memorize the training data, right, including its noise, rather than learning general patterns, right? So overfitting leads to poor performance on new and seen data. And that's why it's so important to monitor both the training and the validation metrics throughout the training process. So to combat overfitting, one widely used technique is early stopping. So this strategy monitors the model's performance on the validation set during training. So if the validation loss stops improving, say for 5 consecutive epochs, then we stop training, even if we haven't reached the total planned number of epochs, right? And why is this helpful? Because continuing to train after the validation loss flattens or increases, this typically leads to overfitting, right? So early stopping not only saves time, but often gives us the best version of the model that generalizes better to unseen data. And so many deep learning libraries like Keras, which we'll talk about today, provides built-in support for early stopping with just a few lines of code. So as you begin building real deep learning models, it's important to use tools that are both powerful and easy to learn. And Keras is a high-level deep learning API that sits on top of TensorFlow. It's widely used in both industry and research for its simplicity and flexibility. So with just a few lines of code, you can define complex neural networks and train them and monitor their performance, right? It is designed for fast experiments, which means you can prototype ideas quickly and test different architectures with ease. So let's take a closer look at how typical Keras model is structured. So in its simplest form, you'll be using the sequential model, which allows you to build your network layer by layer. It's like stacking blocks in a straight line. Each layer feeds into the next. So you start by adding an input layer, followed by one or more dense layers with activation functions, and then finally an output layer, right? And once the model is defined, you need to compile it, right? This is where you specify the loss function, the optimizer, and any metrics you want to track, like accuracy, right? And then you call the fit function to train the model on your data, and later you use the evaluate function to test its performance, right? So this pipeline, build, compile, fit, evaluate, is the core of how Keras models work. So although you'll be working directly with the Keras API, it's important to know that all operations, including the model's creation, training, and evaluation, are ultimately powered by TensorFlow, right? So think of Keras as your user-friendly interface and the TensorFlow as the powerful engine doing the heavy lifting in the background, right? So when you compile or train a model in Keras, it is translated into TensorFlow operations under the hood, right? And it's TensorFlow who takes care of the different tasks that we've discussed, which is training the model or evaluating the model and so on. So let's take a look at a quick demo for how to build a simple neural network using Keras. So in this demo, we will build a simple neural network using Keras to predict whether a passenger survived the Titanic disaster. So this is a binary classification problem, and then our model will predict either class 1 for survived or class 0 for did not survive. So we start by importing the libraries which we will need, and that includes TensorFlow and Keras, and which will be used for building the model. And we're also going to need pandas for handling and pre-processing the data, and scikit-learn also for pre-processing the data. And so we start by loading the Titanic data set, and then we're going to just keep a few relevant features or attributes that we see here, right? The age, the fare, the class, and so on. And then the target variable, which is survival, right? So we also can perform some basic pre-processing tasks like encoding the features. And here we encode the sex feature into a numeric format. We do the same to the class attribute, right? So the first class will be number 1, second class will be 2, third class will be 3. So we always do feature encoding as a part of a pre-processing stage of the data because our models don't understand categorical attributes, right? So everything has to be encoded into a numerical format, right? So now we prepare our data, and what we do here is splitting our data into input features, which is the X. That's what we're going to feed our neural network with. And then the output or the label is the Y. And then we use the train test split function to divide our data set into training and testing. So here we are specifying that we're going to use 80% of the data for training and 20% for testing. And then finally, we scale the input features using a standard scaler so that they all have a similar range. So this helps training converge more smoothly. Next, we use Keras's sequential API to define a simple neural network. It has one hidden layer with 8 neurons, and we're using the ReLU activation. And we have one output neuron with a sigmoid activation, right? This is ideal for a binary classification problem. And then we compile our model using Adams optimizer. We'll talk about more optimizer options next week. And then we define the loss function, which is binary cross entropy. And then we're going to be monitoring the accuracy during training. So we trained the model for 20 epochs using part of the data, which is the training set. And then we use the 20% as a validation set. So this allows us, as we've said before, to monitor how the model is performing on unseen data during training, right? So as the training progresses, Keras reports loss and accuracy on both the training, as you can see here. So this is the training accuracy, and this is the validation accuracy. This is the training loss, and this is the validation loss. So after training, we evaluate the model on the test set, and this gives us a final accuracy score, which shows us how well the model generalizes to new data. Finally, we visualize the training and validation accuracy over epochs. This helps us detect issues like overfitting, as we said, and ideally, we want to see both the training and validation accuracy improve together and then level off.